Fractal Abstract Expressionism. Clouds are not spheres, mountains are not cones, coastlines are not circles, bark is not smooth, nor does lightning travel in a straight line. Benoît Mandelbrot. Fractal geometry will make you see everything differently. There are risks in reading further. You risk losing your childhood vision of clouds, forests, flowers, galaxies, leaves, feathers, rocks, mountains, torrents of water, carpets, bricks, and much more. Your interpretation of these things will never be the same. Michael F. Barnsley. There is, in reality, neither beautiful style, nor beautiful drawing, nor beautiful color. There is only a single beauty, the beauty of truth that reveals itself. When a truth, a profound idea, or a strong feeling, explodes in a literary or artistic work, it is obvious that the style, color, and drawing are excellent. But they only possess this quality through the reflection of truth. Auguste Rodin. Introduction to Fractals. What are fractals? Fractals are complex mathematical structures that exhibit infinite detail at every scale. They can be defined as mathematical sets, geometric constructions, or patterns that display self-similarity and complex detail regardless of magnification. While many fractals can be generated through iterative equations, this is just one of several mathematical approaches to creating these intricate forms. According to Euclid, the Greek mathematician who lived more than 2 millennia ago, the most basic elements of geometry are points, entities that have no size, or rather, that have zero dimension. A line is considered the distance between any 2 points, an entity with a single dimension. A flat surface, like a screen display, according to Euclidean geometry, has 2 dimensions. To determine its area, we multiply its length by its width, assuming these are perpendicular. Similarly, a 3-dimensional object requires multiplying 3 measurements, length, width, and height, to calculate its volume. Euclid's geometry provides an excellent foundation, but it fails to describe many natural phenomena. The contours of mountains, the surface of human lungs, the trajectory of water droplets as they penetrate the earth, countless natural forms cannot be adequately described by traditional Euclidean geometry. For centuries, mathematicians assumed that these irregular, rough features of reality lay beyond mathematical description. The concept of fractional dimensions, formalized by Felix Hausdorff in 1918, offered a breakthrough. These non-integer dimensions allow us to describe objects that exist between traditional dimensional categories, such as a crumpled napkin, which occupies more space than a flat surface, dimension 2, but less than a solid object, dimension 3, giving it a fractional dimension between 2 and 3. This approach provides a mathematical language for describing the complexity we observe in nature. Fractals and chaos theory. Fractals are often related to chaos theory, particularly appearing as attractors in the phase space of equations describing complex phenomena such as weather patterns. However, it's important to note that not all fractals arise from chaotic systems, and not all chaotic systems produce fractal patterns. In Greek mythology, chaos was the primordial state of existence, the unorganized void from which all things arose. According to Hesiod's Theogony, chaos preceded not only the origin of the world, but also of the gods. Modern chaos theory emerged to understand the apparently erratic and irregular fluctuations found in nature, financial markets, and atmospheric patterns. A defining characteristic of chaotic systems is their sensitivity to initial conditions. The butterfly effect, where tiny disturbances in a system's initial state can lead to dramatically different outcomes, making long-term prediction nearly impossible. Despite this apparent randomness, chaotic systems often reveal ordered patterns when viewed through the lens of fractal geometry. The mathematical foundations of fractals. Defining characteristics. The term fractal was coined in 1975 by mathematician Benoît Mandelbrot, derived from the Latin word fractus meaning broken or fractured. While various definitions have emerged as the theory developed, 2 key characteristics define most fractal structures. Infinite complexity. Fractals display endless detail at every scale of magnification. No matter how far you zoom in, new details continue to emerge. This property means that fractals cannot be completely represented in finite form, as their detail is inexhaustible. Self-similarity. Fractals exhibit patterns that repeat across different scales. A small section of a fractal often resembles the whole structure, creating a recursive pattern where similar forms nest within each other. This self-similarity may be exact, as in geometric fractals like the Koch snowflake, or statistical, as in natural fractals like coastlines or mountain ranges. Mandelbrot's original technical definition stated, "A set is said to be fractal if the Hausdorff-Bessicovich dimension of this set is greater than its topological dimension." Over time, mathematicians recognized this definition as too restrictive, leading to broader characterizations focusing on self-similarity and scale invariance. Fractals in nature and art. Natural fractal patterns. Fractal forms appear throughout nature. In the branching patterns of trees and rivers, the structure of snowflakes, the outline of coastlines, the formation of clouds, and even within our bodies in the branching networks of blood vessels and neural pathways. These natural fractals typically display statistical self-similarity rather than the perfect recursion found in mathematical fractals. The ubiquity of fractal patterns in nature suggests that these structures offer evolutionary advantages: efficient distribution networks, maximized surface area, and resilient forms that can adapt to environmental pressures. The ubiquity of fractal patterns in nature suggests that these structures offer evolutionary advantages: efficient distribution networks, maximized surface area, and resilient forms that can adapt to environmental pressures. Fractals in visual art. Abstract Expressionism, with its emphasis on spontaneous creation and emotional intensity, might seem far removed from mathematical precision. However, analyses of Jackson Pollock's drip paintings have revealed fractal patterns with dimensions between 1.3 and 1.9, indicating an intuitive grasp of complex geometrical principles. Pollock's technique of layering paint at different scales created works with statistical self-similarity reminiscent of natural fractals. Mark Rothko's luminous rectangular forms, though seemingly simpler, also display subtle fractal characteristics in their color field boundaries and textural variations. The immersive quality of Rothko's work derives partly from these fractal elements that engage the viewer's visual perception at multiple scales simultaneously. Beyond these pioneering abstract expressionists, contemporary digital artists have explicitly incorporated fractal mathematics into their creative process. Software programs allow artists to explore the Mandelbrot set, Julia sets, and other fractal structures, manipulating parameters to generate intricate forms of astonishing diversity and beauty. The aesthetic appeal of fractals. Fractals possess a unique aesthetic quality that combines mathematical precision with organic complexity. Studies in perceptual psychology suggest that humans display a preference for visual patterns with fractal dimensions around 1.3 to 1.5, the same range found in many natural landscapes. This preference may relate to our evolutionary history, where recognizing natural patterns contributed to survival. The aesthetic power of fractals lies in their balance between order and complexity. As theories of aesthetic information propose, art must strike a balance between predictability and surprise to engage viewers. Fractal forms achieve this balance intrinsically. They contain recognizable patterns that provide coherence, alongside endless variation that continues to surprise and engage. In classical aesthetics, the concept of the sublime describes experiences that overwhelm the senses while engaging the intellect. Fractal art often evokes this response, as viewers confront forms that are simultaneously comprehensible yet inexhaustible. Like mythological monsters, the Minotaur, the Hydra, the Sphinx, fractals combine the familiar with the enigmatic, generating both fascination and a kind of productive unease. Fractals as a philosophical lens. Infinity and beyond. Fractals offer a tangible approach to contemplating infinity. Unlike abstract philosophical concepts, fractal structures provide visual representations of infinite complexity contained within finite boundaries. The Mandelbrot set, for example, contains an infinite variety of forms within a region that can be displayed on a computer screen. This paradox, the infinite within the finite, resonates with philosophical traditions across cultures that have wrestled with concepts of boundlessness and limitation. The fractal perspective suggests that infinity is not merely a distant abstraction, but a principle embedded within the structure of reality itself. Fractals as metaphor. The self-similar nature of fractals provides a powerful metaphor for understanding relationship patterns across different scales. From the perspective of systems thinking, similar organizational principles can be observed in structures ranging from cellular biology to social networks to cosmic formations. This perspective offers a unifying framework for understanding complex systems. In my own exploration of fractal geometry, I've found that these mathematical forms transcend their technical definitions to become windows into deeper questions of existence. When generating fractal music through programs like Fractmas 2000, the experience is less about creating something new than discovering something that already exists mathematically. This raises interesting questions about the nature of creativity and discovery in both art and mathematics. Fractals and collective knowledge. The mathematical nature of fractals challenges conventional notions of intellectual property. While specific artistic expressions using fractal principles may be original, the underlying patterns themselves exist independently of human creation. Like a photographer capturing a natural landscape, the fractal artist documents mathematical truths rather than inventing them from nothing. This perspective suggests that fractal patterns represent a form of collective heritage, mathematical truths that exist beyond individual authorship. The explorer of fractal mathematics becomes a curator who reveals particular views of this universal landscape rather than claiming ownership of it. Fractals as a model of existence. The recursive, self-similar nature of fractals offers a compelling metaphor for human development across generations. Just as fractal patterns repeat with increasing complexity at different scales, human knowledge and culture evolve through iterative processes that build upon previous foundations. This fractal view of human development suggests that our individual lives participate in larger patterns that transcend personal existence. Each generation contains elements of previous generations while introducing new variations and complexities, creating a developmental trajectory that resembles the unfolding of a fractal pattern. From this perspective, the concept of infinity becomes not merely mathematical, but existential. While no individual can comprehend infinity in its totality, the collective human enterprise across generations may approach greater understanding through recursive development. Just as each iteration of a fractal algorithm reveals new details, each generation of human inquiry reveals new insights about existence. In this fractal conception of reality, we are simultaneously unique individuals and participants in larger patterns. The boundaries between self and other, between part and whole, become more fluid. As in a fractal structure, the whole is contained within each part, though expressed differently at different scales. This does not mean that all distinctions are meaningless. Rather, it suggests that boundaries and categories, while pragmatically useful, represent perspectives rather than absolute divisions. In a fractal world, differences in degree can become differences in kind when viewed at different scales of analysis. Conclusion: the fractal perspective. Fractal Abstract Expressionism represents more than a mathematical approach to art. It offers a framework for understanding complexity across domains. From the precise language of mathematics to the intuitive gestures of abstract painting, fractal patterns provide a bridge between quantitative and qualitative approaches to reality. By engaging with fractal structures, we encounter a form of beauty that emerges from truth rather than convention. As Rodin suggested, when profound truths reveal themselves through artistic expression, the result possesses a beauty that transcends style and technique. The fractal perspective invites us to recognize patterns that connect seemingly disparate domains of experience. It challenges linear thinking and simple categorizations, offering instead a vision of reality characterized by recursive complexity and self-similarity across scales. Whether applied to art, science, philosophy, or personal development, this perspective reveals the intricate patterns that connect seemingly separate phenomena into coherent wholes. In the end, fractals remind us that complexity need not mean chaos, and pattern need not mean oversimplification. Between rigid order and formless disorder lies the rich territory of fractal structures, endlessly varied yet governed by principles, complex yet comprehensible, finite yet inexhaustible in their detail. In this middle space, we find not only mathematical beauty, but insights into the nature of existence itself.